In this video, we're going to be talking about the reflection coefficient gamma, which is a physical quantity that tells us how much wave reflected from the load. Now, we need this physical quantity here, and we didn't need it in normal circuits, because there we suppose that everything is perfect, that whatever you would send to the load would get absorbed, and that nothing would be reflected. So now in transmission lines, we have different rules, and one of them is that the signal, the wave that gets sent to the load, some of it gets reflected. Now, of course, in a perfect scenario, we want all of it to be absorbed, but unfortunately, some of it might get reflected. So this reflection coefficient gamma is defined as the ratio between the reflected wave, which we'll call V minus X, and the direct wave, V plus X. So this comes from the voltage Vx in a transmission line that is made out of two parts, which is the direct wave and the reflected wave. And we can write this as A e to the minus gamma x plus B e to the gamma x. Now, I've talked about this more in the introduction video, so if you're interested in it, be sure to check it out. But to sum it up, this right here makes perfect sense that it's the direct wave, and this makes perfect sense that it's the reflected wave, and I'll tell you why. We call x the distance starting from the beginning of the transmission line and going towards the load. And as you can see in this first term, let's write it separately, a e to the minus gamma x. The more we go down the transmission line, so that means the more x goes up, the smaller this term becomes. Okay, so v plus x becomes smaller. And that makes perfect sense because when the wave propagates right here, then we will have some losses normally in the line, and the direct wave will become smaller. And also, this term right here, it makes sense that it's a reflected wave because this term basically represents how the wave comes back in this direction. And as you can notice, the more it goes towards the left, the smaller x is, because we look x from this side and not from this side. So the more it goes towards here, the smaller x becomes, and the smaller this term becomes right here, which is v minus x. And makes sense because also when the wave gets reflected, we will have losses in the line. So now, substituting for the direct and the reflected wave in gamma, we have gamma equals b e to the gamma x divided by a e to the minus gamma x. And notice that this right here from the denominator, we can just rewrite it as we will rewrite b divided by a, we will rewrite e to the gamma x, and this is also right here e to the gamma x. So we'll have e to the 2 gamma x. And seeing here that a and b are complex constants, and which means that they have their own module and phase, but they're still constants. And this formula right here, I'm just gonna write gamma x because it depends on x, is true for all x in the transmission line. So that means that we can substitute, for example, x equals 0, and we will get a new interesting formula. And if we substitute, we have b divided by a multiplied by e to the 0, which equals 1, so we will just leave it like this. And we can call this thing right here gamma in, okay, since it's at the input of the transmission line, at the beginning of it. So since this a and b are constants and they're the same for the whole transmission line, we can also rewrite the original gamma x as this right here is gamma in, so we just write gamma in e to the 2 gamma x. Okay, so we've got our first important formula. But sometimes it's much easier to resonate not with x, so not from the beginning of the transmission line, but from the end of the transmission line, and we will call this x prime. So the reason being is because, for example, sometimes it's difficult to measure things at the generator, and it's easier to measure them at the load. A practical example is a TV and an antenna. Let's say the antenna is our generator and the TV is our load. It's much easier to just go near the TV and measure something rather than go on the rooftop and measure something at an antenna. So that's why it's very useful to have a formula with x prime, which means from the load, and they are used pretty often. So this length right here of the transmission line, let's call it L, and we can say here that x plus x prime equals L. And if we isolate x, we have that this is equal to L minus x prime, okay? So seeing that we expressed x in a different way, we can just substitute in our already existing formula. So we have here that gamma x was equal to b divided by a e to the 2 gamma x. And now, if we substitute for x, we will write it as L minus x prime. That means that also here we will substitute L minus x prime. So this is equal to b divided by a e to the 2 gamma L e to the minus 2 gamma x prime. And this formula is also true for all x prime in the transmission line. So now we can do the same trick as before, since these right here, they are still constants. So we can substitute for x prime equals 0. So we can just call this x prime for simplicity to not get confused. And this is, if we substitute for 0, we have b divided by a e to the 2 gamma L, multiplied by e to the 0 minus 0 is equal to 1. So we'll just leave it like this. So this right here, we will call gamma L because it's at the load. So this is the reflection coefficient, basically, at this part right here, when x prime is equal to 0. So we can now substitute this part at the formula, and we will get that gamma x prime equals to gamma L e to the minus 2 gamma x prime. So we got our second very important formula that is from the load part, and that will help us massively calculate things. So that's it for today's video. I hope you enjoyed it. Ask any doubts you have in the comments, and see you in the next one.